It's glowing from leftover heat from when it was an authentic star. The sun will die as a white dwarf. When the sun in 5 billion years sheds all of its outer layers, it will reveal a dense core about the size of the Earth. That will be a white dwarf that will slowly cool over the eons. But this white dwarf is in a binary orbiting system with the red giants. And red giants like becoming bulbous, and they keep expanding and expanding. And there's a balance point, a literal balance point between these two objects where...
So why can a dead star become one of the brightest tools for measuring the entire universe? Imagine something about the size of Earth, with roughly half the mass of the sun, still glowing with leftover heat. That is a white dwarf, the exposed core of a star that has burned through its nuclear fuel and blown off its outer layers. Its matter is squeezed so tightly that atoms lose their usual structure and electrons form a highly compressed gas. The pressure holding it up is called electron degeneracy pressure, a quantum effect. When electrons are forced into the same region of space, the rules of quantum mechanics prevent two identical electrons from occupying the same state. By itself, this stellar remnant just cools and fades, hardly an obvious candidate to light up the cosmos, yet it is the starting point for one of astronomy's most powerful distance markers. A dead star can become dramatically active if it has a companion. Many stars are born not alone, but in pairs orbiting their common center of mass. This arrangement is called a binary system. If one of them ages into a swollen red giant, its outer layers expand until its own gravity can barely hang on to them. There is a region around each star, a kind of gravitational territory, called its Roche lobe. Inside it, material stays bound to that star. Outside it, the material can be pulled away. When the red giant's outer gas stretches beyond this boundary, the white dwarf's gravity can capture it, drawing gas off its partner through a narrow bridge of matter. Instead of peaceful cooling, the dwarf is now slowly gaining mass, surrounded by a disk of spiraling hot gas on its way down to the surface. What stops that white dwarf from just piling on mass forever? Gravity pulls it inward, tending to crush it smaller, while electron degeneracy pressure pushes back, and for low masses, those two effects can balance. But in the 1930s, calculations showed there is a maximum mass where this quantum pressure can still counter gravity. Above that, gravity dominates. That upper limit is called the Chandrasekhar limit, and it is about 1.5 times the mass of the Sun, packed into an Earth-sized sphere. Because the physics of electrons and gravity are the same everywhere, this limit is nearly universal for carbon-oxygen white dwarfs. This universality is the first hint of why these dead stars, in death, can behave in such a predictable way that we can use them as cosmic measuring sticks. When a white dwarf approaches that limit, the balance fails and its interior ignites. As fresh gas accumulates, its central temperature rises until carbon and oxygen nuclei in its interior can fuse again. But now, there's almost no thermostat. In an ordinary star, if the core gets hotter, it expands and cools, regulating the fusion rate. In a degenerate core, pressure barely depends on temperature, so when fusion starts, nothing expands in time to slow it. The result is a thermonuclear runaway. Within seconds, a wave of uncontrolled fusion moves through the star, releasing enough energy to unbind the entire object. This event is called a Type Ia supernova. For a few weeks, that tiny remnant can outshine billions of normal stars, yet it leaves behind no core at all, just an expanding cloud of heavy elements hurtling into space. How does such a violent, chaotic explosion become a precise tool for mapping the cosmos? The key lies in that Chandrasekhar limit, because even though they can arise from more than one kind of progenitor system, these supernovae typically ignite under broadly similar thermonuclear conditions and burn through comparable amounts of white dwarf material. The total amount of fuel and the conditions of ignition are remarkably similar from system to system. That means their true brightness, the amount of light energy they release, is nearly the same. Astronomers call such an object a standard candle, like a light bulb whose wattage you know in advance. If you see a standard candle and it looks faint, you infer it is far away. If it looks bright, it is closer. By comparing how bright a Type Ia supernova appears to how bright it must actually be, we can calculate how far its host galaxy is from us, even when that galaxy is far beyond where individual stars can be resolved. These explosions did more than give us distances. They changed our prediction for the universe's future. In the late 20th century, astronomers measured Type Ia supernovae in very distant galaxies and found them dimmer than a slowing expansion would allow. The best explanation is that space itself is filled with something we call dark energy, a form of energy that makes cosmic expansion accelerate rather than decelerate. The route from a crushed quantum-supported core to accelerating space shows how tightly small-scale physics and large-scale cosmology are linked. There is also a chemical consequence. These same supernovae forge and disperse many of the heavier elements that ordinary stars are less efficient at making. So the dead star that once simply cooled in the dark becomes, through a binary partnership, both a factory for the atoms in our bodies and a beacon that lets those atoms, assembled into minds, measure the universe that created them. Like if this was interesting, hit the subscribe for more and turn that notification bell on.